Uh, First of all, I would like to thank the organizers for this nice workshop and for giving me the opportunity to present my work here. Today, I will be talking about one of the aspects of gravitational wave called gravitational wave memory and its derivation in the frequency space. Professor Mohanty has extensively discussed the formalism. I'll give some of the results, and the talk will be based on this paper. The talk will be based on this PhD paper, which has been done in collaboration with Professor Subhendra Mohanty, Dr. Suraj Prakash. So this is roughly the plan for today's talk. First, I will begin with what is called the gravitational wave memory, and then what are the types of memory that we have depending upon the source. And next, I will briefly sketch the field theoretic way of deriving the memory signal, followed by a comparison of the memory waveform constructed using the soft graviton theorem. Finally, I will conclude with the advantages of this field theoretic approach in compared to the traditional quadrupole way of deriving the memory. So, okay, to start with, this is the gravitational waveform that has been detected long back in 2015 by two LIGO observatory, one is Hanford and other is Livingstone, and the other in Livingstone in 2015, and the signal they named as GW150914, I think. And the waveform, they matches exactly with the prediction of general relativity of gravitational wave emanating from the merger of two black holes. Now, if you see the waveform, it starts from 0, then oscillates for a few cycles, again basically goes back to 0. So this is the waveform, a gravitational waveform. Now, if this kind of gravitational wave hits the detector, basically the detector arms, they stretch in one direction and squeeze in other direction. But as the gravitational wave passes by the detector, these test masses or the detector goes back to its initial state as the gravitational wave passes by. But this is not the complete story, because like in reality, all the gravitational wave sources, they must possess some source of memory. So what is the memory that I will discuss next? Now, for a gravitational wave with memory, the strain starts from 0, oscillates for a few cycles, and then again return back, settle down to a non-zero values. Now, how we'll see this in the detector? Basically, when a gravitational wave with memory passes through the detector, it causes a permanent displacement of the detector. So basically, leaves behind the memory of this the wave that passed by, and the residual displacement of the detector, that is called the memory. And in case of normal gravitational wave, basically this causes a oscillatory deformation. Basically, as the gravitational wave passes by, the detector returns to its initial state. So this is the difference of a gravitational wave with memory and the without memory. Which one? No, this is not. This memory has not been observed yet. And depending upon the source, there are two kinds of memory. One is linear memory and the other one is the non-linear memory. And this linear memory mostly arises in the case of non-oscillatory motion of objects. For example, the binaries in unbounded orbit like hyperbolic orbit or neutrinos for supernova. And the thing is, Professor Mohanty discussed gravitational wave from the radio burst, gamma ray radio burst. In those cases, they gives the linear memory. And for the non-linear memory arises from a secondary gravitational wave that has been sourced by primary gravitational wave. And this kind of non-linear memory arises, they appear from the oscillatory motion of objects. For example, the binaries in bound orbits like circular orbits and elliptical orbits. With this brief introduction, I'll briefly sketch this field theoretic way of deriving the memory. Professor Mohanty has discussed in his two lectures the formalism extensively, so I'll briefly sketch this thing. And while deriving the memory signal in field theoretic way, in field theoretic treatment, we basically calculate the amplitude of a graviton emission from the binaries. And the probability amplitude for emitting a graviton with this polarization epsilon mu nu from a source with stress tensor T mu nu is this this is the amplitude. This kappa is square root of 3 pi g, and this epsilon is the polarization, T mu nu is the stress tensor of the source. Now with this probability amplitude, we can calculate the gravitational waveform, and in frequency space the stress tensor and gravitational waveform has this relation, and like many people discuss this thing, like this lambda IJKL, this is the projection operator, the transverse stress projection operator, TKL is the stress tensor in the frequency space. Now real example is the calculation of linear memory from hyperbolic encounter. So basically in the hyperbolic encounter we consider a black hole of mass m1 in a hyperbolic orbit. This is orbiting around a larger black hole of mass m2. Now in this setup, if we calculate the stress tensor component in the frequency space, they are basically this function of this Henkel's function and their first derivatives. Okay. Now next week on January 8, Indranil Chakraborty, he will discuss the linear memory from the supernova neutrinos from the other source. Okay. Now with this stress tensor in the frequency space, we can estimate the memory waveform in the frequency space. But what we actually did, we have this memory waveform in the frequency space, then we do a Fourier transform, and this is how the memory waveform in the time domain. This is the linear memory waveform for a hyperbolic encounter. This is the memory waveform, how this looks like in the time domain. Now if you see, like this is a theta function. Now if you perform an inverse Fourier transform of this theta function, that will give you the memory waveform in the frequency space, and this behaves like 1 over omega. Okay. Next I will discuss the connection between this memory, this field theory calculation with the waveform constructed using the soft graviton theorem. What soft graviton theorem tells us about, like soft graviton theorem tells us that a graviton emission from a n scattering, the amplitude of a graviton emission from m scattering, that can be expressed as the products of a kinematical factor A and the amplitude of a n scattering, like n particle scattering. And using that soft graviton theorem, Professor Ashok Sen, Professor Alok Ladda, and Dr. Bishwajit Sahu, they have derived the memory waveform, and that memory waveform has that kind of, they are the function of 1 over omega and log omega. Now in our case, if we expand this T mu nu, all this stress tensor in the zero frequency limit, we also obtain the same kind of behavior in our derivation. We have this 1 over omega behavior and this log omega behavior, not only the functionally, but these factors, this Aij and Pij, which are the function of this incoming momenta, these with the appropriate like substitution of the momenta, these factors also matches exactly with the result. So we found an agreement of our calculation of linear memory in frequency space using this field theoretic calculation with the results obtained from the soft graviton theorem. Okay. Finally, I will discuss this nonlinear memory from the circular orbits. Again, we have like two masses m1 and m2. They are orbiting in a circular orbit, and the orbit is in the xy plane. So that's why there is no zz component also in the earlier case also. And that stress tensor in the frequency space, it looks like this. Now if you use this stress tensor to calculate the memory signal, and this is the memory signal, this is how the memory signal looks like, and this I is the angle between the direction towards Earth and the direction of the orbit. Now if you want to understand this signal in the case of a physical inspiring binaries, and this Tc is the time when the innermost circular orbit is reached during the merger, beyond which we can't apply this formalism. Now if you see, like when it at very early time, so there we have a non-vanishing memory. As this T prime approaches this Tc, the memory grows, and eventually settles down to a like maximum value. And this is the time when the two objects they merge and coalesce into a single object. Okay, I'll conclude with the summaries. This our field theoretic calculation, they produce all the results as obtained from the classical quadrupole formula, and this field theoretic calculation gives us the waveform directly in the frequency space. And these frequency domain templates, they are very useful for extracting signal from the actual data. And our full orbit calculation in the field theoretic method, they matches exactly with the results from the soft graviton theorem. Thank you for your attention and wish you a very happy new year.
We have a few questions.
Can you go back to the first two slides where you said the detection of memory based is
This one?
different? Yeah. So what is the main difference between these?
Okay, if you see this, like at very early time, it starts from 0 and oscillates, and then again it goes to 0.
Okay.
And if you see in this case, it starts from 0. This is the waveform, and this is the memory waveform. There is a constant memory waveform, this is 0. This is increasing, but at later time, it does not return to 0. If this is the difference, like if the wave does not have a memory, this blue is this blue signal is the signal. But gravitational wave with memory, there is permanent displacement between these things. So basically,
what kind
residual separation.
Okay.
Like if the gravitational wave does not have a memory, the signals should return to this value. But in terms of the, if you want to calculate in terms of polarization, if you calculate the polarization at far infinity and past infinity, if the gravitational wave does not have a memory, the difference should be 0. But for a gravitational wave with memory, the difference is non-zero basically.
So I didn't quite catch if, I have a bunch of questions. How long does it take you to calculate the waveforms?
How long?
How long is it taking you to generate? You're generating waveforms as well, right?
No, like we no.
Okay, so you skip the waveform calculation altogether. You just assume the waveform from whatever has been done before. Like
for the circular wave, this is the relation with that time domain.
Yes. Okay. Okay. I think that answers most of my questions. All right. The other thing I was wondering is, have you thought about extending this to things like gravitational wave memory from bursts? Because that's something we have searched for in PDA data. And
from the gamma ray burst?
No, bursts from the cusps of cosmic strings.
No.
Are there more questions?
So, what if, is it possible that, I mean, you have this one particular projectile which goes around the black hole and it creates a memory, and much later, if another projectile comes in the reverse direction, is it going to wipe off the memory, or? So I'm talking about two consecutive events where a memory is created, and the question is that can it be wiped off by another sort of event?
It should be a cumulative effect, I think.
So it can reduce, right?
Yes. So that's depend.
Will that depend on the direction of from where the gravitational wave is coming? Since
we are measuring the difference,
yeah,
that we have to see. Like I can't comment now whether it will decrease or like enhance. That we have to see. Like, but it will surely change. Like.
Okay, so multiple events with memories can actually have a cumulative effect. Okay. Thank you.
So if there are no more questions, let's thank Arpan again.